So hello everyone, my name is Rodney Lalone, and I'm going to be presenting this paper called Understanding Deep Learning Requires Rethinking Generalization. It's by the following authors here who were all working at Google Brain at the time. And this was selected as one of 3 papers to be named for ICLR Best Paper Award for 2017. So it's very...
17, not 16. Somebody said 16.
Nope, 2017
17.
Best Paper Award,
Okay,
ICLR, yep, correct.
Good.
So I'm going to outline the presentation. So first we're going to talk about the motivation for this work, what they're trying to examine, some important background information so you guys can understand the implications of the work, the experimental findings that they present, and then discussions on those experimental findings, talking about the implications of them. So what is the motivation? They're trying to answer one simple question. And that question is, what is it then that distinguishes neural networks that generalize well from those that don't? That's the main question they're trying to answer with this work. Okay, so one more time. What is it that distinguishes neural networks that generalize well from those that don't? Some background information we're going to talk about. We're going to talk about generalization so you guys have an understanding of what that is. Some theoretical concepts about model capacity, and then talking about regularization, explicit, implicit, and different techniques in there. So generalization error is defined as the difference between training error and test error. So if we have the plot at right, the training error is marked by the red curve, and the testing error is marked by the green curve. This distance here would be the generalization error at this point in training, which is 0.1. If we train further, we can see the error grows to 0.2. Training even further, that error grows even further to 0.3. So this model here is likely overfitting, and the training error and the testing error getting further away from each other. So now we're going to discuss some of more of the theoretical concepts about model capacity, and that's basically the flexibility of a network and all the different types of input that it can fit to. So an important starting point for that is this universal approximation theorem. And the universal approximation theorem states that a feed-forward network with a single hidden layer containing a finite number of neurons can approximate any continuous function on compact subsets of Euclidean space. And George Chibanko proved this for sigmoid activation functions in 1989. What this unfortunately doesn't give us any information about is the algorithmic learnability of those parameters. So hopefully everyone understands the implication of this. It's basically saying that if you have a single layer neural network, we can approximate any possible continuous function with a single layer. Okay. But we might not necessarily be able to learn the weights of that layer very effectively. Okay, hopefully that makes sense to everybody. Moving on, we're going to talk about VC dimension. This is getting further into this idea of model capacity. So VC dimension, we say a classification model F with some parameter vector theta is said to shatter a set of input points x1 to xn if, for all assignments of labels to those points, there exists a theta such that the model F makes no errors when evaluating that set of data points. Okay, so we have a model. That model has parameters. We can label certain input data x1 to xn perfectly given that model with those parameters. If that's the case, we have shattered that set of data points. How does, go ahead.
So this says this is about the testing of the classifier.
No, this is just for training.
For the training.
Yeah, this will be just for anything. Any given a set of data points, we can perfectly label those data points given a model.
But I mean, training, the labels are known, right? When we train a network classifier, so we know the labels. The only thing is that the network or classifier will be able to label the data we're testing.
No, at train, so we're talking about model capacity. So this is the ability for the model to label all the data. So imagine our model is just a simple linear classifier. we won't be able to label all of our data points with a simple linear classifier. We need a more complicated model to be able to label all of our data points.
What does labeling means? Labeling a data means what?
So given an input, assigning it to the proper output.
Like imagine 1,000 classes.
Sure, so we have 1,000 classes and 1,000,000 different inputs.
Yeah.
So the model capacity, if we can perfectly label all 1,000,000 of those inputs to the proper 1,000 category label, the model is said to shatter those 1,000,000 inputs.
That's right. But what I'm saying, see that when we do the training of that model, when we train image, there we already have assigned labels to that data, right? So it will be more meaningful that the model is assigning the labels during testing. The right or not correct?
So that's how it relates to generalization. But the point is does the model have the capacity? Does there exist a set of parameters theta that could perfectly label those data points, right? So if we change our parameters, we could perfectly label those testing points, right? So if that's the case, if we could perfectly label all those testing points with some possible set of parameters, then that model that we have would shatter those inputs. Cool. So hopefully that makes sense. So kind of what Dr. Shaw was getting into, alluding to how VC dimension relates to model capacity, or how this relates to model capacity, is the VC dimension of a model F is the maximum number of data points that can be arranged so that F shatters them. Right, so this makes sense. So we have a model, and we have some input data. Say we have 1,000,000 different images. If F can perfectly label all 1,000,000 of those with some setting of the parameters, then F shatters those 1,000,000 inputs. Say we have 2,000,000, say we have 4,000,000, say we have 8,000,000, et cetera, et cetera. There's going to be some point at which F can no longer model, can no longer perfectly label all of our possible inputs. Whatever that top number is, whatever the maximum number of data points that we can perfectly label is, that is the VC dimension of our model. Cool. So here's an example. We have a very simple linear classifier. We're trying to draw a line to separate these into two groups, blue pluses, red minuses. Okay, so we can draw a line here, we can draw a line here, we can draw a line here, right? So given some set of input points, there is a learned parameter set theta such that we can draw a line and perfectly separate these. Once we move to 4 points, there exists possible input data such that we cannot possibly separate them given any possible setting of the parameters theta. So given any possible setting of a linear classifier, we cannot possibly separate these into two groups, right? Because here you see there are three groups, right? Blue, red, blue. Right, so the VC dimension of this linear classifier would be 3. 3 is the maximum possible number of data points that we can label. Cool, okay. So how does this VC dimension sort of relate to the idea of generalization performance and generalization error? So we can use VC dimension to compute a probabilistic upper bound on the testing error. And so what that looks like is here. So the probability that the testing error is less than or equal to the training error plus this constant is given by 1 minus eta. Okay, and here n is the number of our input data points, and d is the number of parameters in our model. Okay, so we can use this idea of VC dimension and this relationship to put a bound on the generalization error. The only issue with this is when it comes to neural networks, this relationship only really holds when the number of parameters is far fewer than the number of samples. And with neural networks where we have typically parameters far greater than the number of input samples, this relationship becomes meaningless. This root here becomes unreal, complex, it becomes a complex solution. And so we can't use this sort of probabilistic upper bound when we start talking about neural networks where we have tens of millions, if not hundreds of millions of parameters. So that's some good background information, and hopefully you guys will remember all of that once we get into actually the findings of the paper. But first we're going to take a little detour to regularization. There's explicit regularization such as weight decay, dropout, data augmentation, and there's implicit regularizations such as early stopping, batch normalization, and even SGD may be doing some sort of implicit regularization that we'll talk about. So weight decay, or L2 regularization, what this is, here's a standard weight update that I'm sure you guys are all familiar with, right? We have the weight, we have some weight in our network at some time t. We have our learning rate eta at some time t, right? The learning rate can change over time. And we take the derivative of the loss with respect to all of our weights, and we can update this specific weight based on the derivative of the loss, and we get a new weight. Right, so that makes sense. Standard backpropagation, right? We compute a loss, take the derivative of the loss with respect to all of our weights, and we update each individual weight based on what our learning rate is at the current moment. We can add a term to our loss such that our lambda here is going to be this weight decay parameter. And what that looks like once it's put into our weight update is we get this extra term over here. And this extra term is an additional subtraction that's going to make our weights lower. And the punishment of that is based on how high the weight is and how strong our weight decay parameter lambda is. So if the weight itself is higher, it's going to be punished more. If our lambda is high, it's going to be punished more. And what this basically does is it forces all weights to become small, hence the term decay, weight decay. Right? So this is going to push all of our weights closer to lower values. It essentially keeps any weight from getting too out of control. Right? And the neural network from favoring individual neurons very strongly. Right? So it's a type of regularization technique. Another common type of regularization is dropout. So in dropout, we randomly drop neurons from layers in the network. You can see here these marked by X's, where we're no longer using those neurons. And this will remove the reliance on individual neurons. So we can imagine this is a binary classification of, is this a person or not a person? And at this last layer, maybe our highest level features are things like a neuron that's learned to detect faces, a neuron that's learned to detect arms, a neuron that's learned to detect legs, something like that, right? You can imagine the case where this neuron that's detecting faces dominates the final value, right? All of these weights can be low, high, it doesn't really matter because the weight on this one right here is the one that's going to really determine what the final say is. Because imagine in our training set, all of our people have a face present pretty much every time. And it's learned that face equals person. But in our testing set, maybe they're turned around. Maybe the face isn't there in the testing set. Now the performance of this is going to be very terrible. Right? So we try and force the network to become not reliant on individual neurons by randomly dropping them. So this can do one of two things. Either it'll learn redundancies. So now our last layer is going to be face, 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 face. And it learns that if we drop them, that's okay because I got 5 other face neurons anyway. Or hopefully what it'll do is it'll learn a more nuanced set of feature descriptors. So now it'll learn that, hey, the face may or may not be there, but if arms are there and legs are there, it's also probably a person. So don't rely so heavily on this face neuron. Try and rely on all the neurons a little bit more equally. Right? So we regularize the weights of the network by forcing it to rely on all different kinds of neurons rather than allowing the weights of certain neurons to dominate our output. Cool, so hopefully that makes sense. Another common method of regularization is data augmentation. So these are domain-specific transformations on the input data. If we're dealing with imaging data, those are things like shown in the figure here, flipping, rotating, cropping, color jittering, edge enhancement, fancy PCA methods, other things like adding random noise, zooming, shear, even elastic deformations. These are all different things that we can do to attempt to increase our input space. So the input space is all possible images that we could imagine that we want to test on later. Okay? So if we train on some set of images, and then we test on an image that's very, very different from any of our training images, the network is likely going to perform very poorly on that. It's not going to know where to put it, right? Because a neural network is just a functional mapping. It's not going to know where to map that in high dimensional space very well. So we want to increase our input space as much as possible at training, so that at testing, hopefully that testing image will fall somewhere in our expanded input space, and the network will know how to map that to a proper space in high dimensional space, in our embedding space. Cool. So hopefully that makes sense. And again, that's what we're trying to do, right? We're trying to increase the input space. And this acts as a sort of regularization. So I'm going to take like 20 seconds here to let everyone soak all of that in. So that's all the background information. Hopefully you guys either knew that or you understand it now. And then now that you guys have all of that understanding of model capacity, generalization, and regularization, we can talk about the findings in this paper. So, the experimental findings. So they do a series of tests, these randomization tests from statistical learning theory. The initial test is exactly what we usually do, right? We have training data, we have labels for that data, and we train a network to classify all of these pictures as dog, right? And we have other classes of human, monkey, whatever, right? We'd have other training samples of those. Then they look at partially corrupted labels. They say, if we randomly select some percent of our training data, say a fifth, and instead of automatically mapping those to the true label, we randomly sample uniformly from all possible labels and pick that. So you see 2 of our labels have changed, and we've just randomly grabbed some other label to map it to. We can also look at random labels where you take this to the extreme. So now every single image that comes up, we uniformly sample from all possible labels, and it looks something like this, right? Where some may happen to map to the right label, some may happen to map to the wrong labels. Another experiment that they do is shuffled pixels. So here we have our input images. We learn some permutation on the pixels of those images, and we send the image through that permutation, and we get an output. Okay? And what that looks like here, that looks like that, right? So these are permutations of those input pixels. Basically, you just shuffle the input pixels by some specific shuffling. Random pixels takes that a step further, and now instead of a specific permutation that's ran on all training and testing images, every training and testing image learns its own individual permutation. Now it looks like that. And then finally, they take Gaussian noise from the original data set that had the same mean and standard deviation of the original data set, and they sample random noise from this Gaussian distribution.
And those may not look like in the image.
No, it looked probably like this. So these images here are random samplings from this specific Gaussian distribution, which is the Gaussian distribution of these images. Right, so these are all, this isn't just random noise. These are actually the permutations of those images. And this is actually drawn from this Gaussian distribution. So what are the results of these randomization tests that they ran? So here you can see the average loss at training time versus thousands of steps. As you can see, the true labels, we're able to fit to them pretty quickly and converge to 0 training error. We can perfectly label all of our training images. With shuffled pixels, random pixels, and Gaussian, we can still perfectly fit. It takes a little bit longer, but we can still perfectly fit all of these, which is pretty impressive, right? Because we're just grabbing samples of Gaussian noise, and we can perfectly label those samples. And then even when we start corrupting the labels, all the way to the point of random labels, we're still able to perfectly fit random labels. And this is pretty astonishing because once you randomize the labels, you completely destroy any relationship between the image and the label. So drawing abstractions across a class of images now becomes impossible because there is no relationship between the image and the label, right? And we can still fit them perfectly. And we'll talk about the implications of that. Time to overfit, this is pretty remarkable. So the x-axis is label corruption. At the right is completely random labels. At the left is completely perfect labels. And as you can see, the networks take a little bit longer to fit to the data when it's completely random, when there's no more relationship between label and image. But we're still able to perfectly fit them to zero training error in not much longer. Some constant factor of time, right? Maybe it's about 1.5 times as long to 3.5 times as long, but it's not much more. It's some small constant factor. And finally, test error versus label corruption. So again, this is the same x-axis as before, but now we're looking at the testing error. So this is generalization. All three of these networks had perfect training error of 0. So the y-axis here actually does represent exactly the generalization error. And the interesting thing about this plot is that network choice seems to make a big influence on generalization error. Cool. So the conclusions and implications of this. So the conclusion is that deep neural networks can fit random labels, which was a little bit surprising. ImageNet, you have 1 million images, 1,000 different labels, and even when we completely destroy the relationship between image and label, we can perfectly fit them, which is pretty crazy. The implication is that the effective capacity, so we talked about this, right, the idea of model capacity. The effective capacity of neural networks is sufficient for memorizing the entire data set. So this was a pretty interesting finding, that these neural networks can really memorize millions and millions, or millions of images and label combinations. And that optimization on random labels remains easy. So this was pretty surprising. They thought that the reason we're able to optimize so quickly is because the network is learning abstractions between classes, and that if it had to literally memorize every single example, that would take much longer to converge than if we were just learning something about the relationship. But it turns out that's not true. Memorizing takes pretty much just as long as learning these relationships and a proper functional mapping between image and label. So that's about model capacity. Now we're going to talk about regularization a little bit. So they run these regularization tests. Here they're examining the different types of explicit regularization, which are data augmentation, weight decay, and dropout that they're investigating here. As you can see, these 3 lowest curves are your testing. Blue is with all 3 methods. The red curve is data augmentation and dropout, no weight decay. And the orange curve is none of them at all. And the important takeaway here is that there is not a very significant difference in generalization performance between using regularization and not using regularization. It certainly helps, but not as much as they thought it would. And I'll talk a little bit more about that. The other thing is batch normalization. So this is with and without batch normalization. As you can see at test time, the results are very similar to each other. The one thing to note is the training without batch normalization tends to be much noisier. You can see a much smoother curve when you have batch normalization, but it really doesn't help much in terms of generalization performance. So again, conclusions and implications. So the conclusion is that augmenting data shows a more significant jump in generalization performance than does weight decay. That we find the biggest gains when we change the model architecture. So here you can see a difference between 0.5 and almost 0 when we look at 2 different model architectures. But if you remember back here, when we look at regularization, we're getting at most about 0.1, 0.2. right? So the model architecture seems to be playing a much more important role in generalization than does these regularization techniques. What does this imply? It implies that explicit regularization may improve generalization, but it is neither necessary nor by itself sufficient to guarantee good generalization. Cool, moving forward. So the implicit regularization, early stopping could potentially improve generalization. You see on the right plot, if we used early stopping at any of these earlier points here, we would actually have worse performance than at the end. So depending on how patient we are with our early stopping, right? So here, if we set our early stopping patience to around 2,000-3,000 iterations, if after 2,000-3,000 iterations it doesn't improve, we'll early stop, right? That would give us bad results. We'd be way down here. But if we wait longer, it doesn't hurt us. So, and then they show here on the plots on the left that had they early stopped, these shaded regions show what the final generalization or the final testing performance would be if they performed the early stopping, right? So here in this case, early stopping does help. Here on the right, early stopping doesn't help and could potentially hurt depending on how sensitive you are with that parameter. The second observation is that batch normalization, although not explicitly designed as a regularization technique, that's not its primary function, it does seem to help generalization performance a little bit. It does seem to perform a somewhat implicit regularization when you look at the training curves. Right, it's giving a much smoother training curve. So it's regularizing the training a little bit. Cool. So what is the author's conclusions? Both explicit and implicit regularization could help improve the generalization performance. However, it is unlikely that regularizers are the fundamental reason for generalization. Okay, so that's the takeaway from this entire paper. If you had to sum it up in one half sentence, it would be regularizers are unlikely to be the fundamental reason for generalization. Okay? And this was a pretty big discovery. Okay, for a long time in the community, it was thought that when you're trying to fit to an enormous possible input space, that the only really good way of guaranteeing convergence and guaranteeing good generalization performance is to use these regularization techniques, which limit your possible search space, right? Because we have tens of millions of parameters that we can set. And there's a combinatorial huge number of ways that we can set them, right? If we don't limit that search space in some manner using regularization, then we'll never be able to get good generalization performance. And what they show in this paper is that no, even without any regularizers, we're still getting good performance, and the regularizers only help just a little bit. That really it's something inherent to the model architectures themselves and inherent to how we're doing the learning itself, not the regularization techniques. Okay, so that's the main conclusion, and then they do two kind of side notes that I'm going to talk about here. So one of them is finite-sample expressivity of neural networks. So everything in literature up until this point was really been focused on the population level. What I mean by that is basically given infinite number of input images, how does the network perform? Right, and given that case, we find that depth K networks typically perform better than depth K-1 networks. Right, and hopefully that makes sense, right? The deeper the network, the better it performs, typically assuming you have enough data, right? Assuming you have unlimited data, deeper networks perform better. Okay, but we don't in practice have unlimited data. So we really need to get a measure on, given some finite amount of data, how can we start to discuss generalization performance, test error? How can we start to bound these things and say, I guarantee the network to perform this well given some finite amount of training data? So given a finite sample size n, even a 2-layer neural network can represent any function. Once the number of parameters exceeds the input sample size. And so say it explicitly, they have this theorem in the paper, right? There exists a two-layer neural network with ReLU activations and 2 times n plus d weights that can represent any function on a sample size of n in d dimensions. Okay, so we're going to actually dig into this and look at this theorem. So we have a network C. That network can represent any function of sample size n in d dimensions if, for every sample S in d-dimensional space, with the number of elements in that sample being equal to n, and every function f maps us from that sample to a number, right, in a real number, right? So we're doing a labeling. There exists a setting of the weights of C such that C can equal that function for every possible input. Does that make sense? So we have a function that labels these samples, and we can set the neural network's weights to give us the exact same labeling that f does. And we can extend this to deeper networks. Here, if we have Decay network, then our width becomes n over k, on the order of n over k.
So C basically is the function. It's giving
C, yeah, so C is our neural network,
Yeah.
and the neural network acts as a function.
so it's just acting as a function.
Yeah, so the big thing and what the theorem was saying is that there must exist a setting of the weights such that we can give the exact same output that f does for any possible function. So hopefully that makes sense. So that's basically an extension. Again, we talked in the background about the universal approximation theorem. That's an extension of the universal approximation theorem to 2 layers with ReLUs.
So that is not their theorem. It's somebody else.
The universal approximation theorem,
That's the previous one. The one.
this theorem is theirs.
That's there.
This is their theorem. And they prove it in the paper. Yeah, so this is an original theorem that they have. And it's an extension to the universal approximation theorem. So appeal to linear models. We're going to talk about linear models really quickly because linear models tend to be a little bit easier to manage, even though they themselves can still be tricky. And hopefully what we learn about linear models can maybe give us some intuition about these deep neural networks. So that's kind of what this next section is going to focus on. All right, so we're going to look at linear models. Imagine we have n data points that are xi is our d-dimensional feature vectors, and yi is the label of that feature, right? So you imagine we have an image, it's d-dimensional, right? Or you can think about we already passed the images through something to get just a d-dimensional feature vector. So we have these feature vectors, we have labels. We want to solve this minimization problem where it's a very simple linear classifier. We have a weight matrix, we multiply it by our input, and we compute the loss between that multiplication and the label that we want, right? So we're trying to set the weights of W such that this multiplication gives us the least possible loss with our labels, right? And this loss function can be a simple mean squared error or whatever you'd like it to be. And the theorem that we just had shows us that if we have n greater than d, we can fit any labeling. Right, so let X denote the n by d matrix whose ith row is xi transposed. Then if X has rank n, meaning all of our samples are linearly independent, then X times W equals Y has an infinite number of solutions. And this linear equation right here is what we want to solve to find a global minimum of our loss function on the previous slide. So we're trying to find this minimum. To find the global minimum, we need to solve this equation that has an infinite number of solutions. Okay? So we're going to look at how SGD is used to solve this equation and what type of solutions SGD converges to. And then maybe that'll tell us something about what SGD is doing, and maybe it'll give us some insight into using SGD to train deep neural networks. So we already know our weight update formula for SGD. Here E is just the loss. Instead of the partial derivative, I just wrote E. When we put this in, we see that W is going to be the sum of the parameters of our network times our data samples. Okay? So we're still trying to learn these coefficients, right? Here they're represented by an alpha. So therefore we know our weight matrix must lie in the span of our data points. And our weight matrix is the transpose of that X, right, where X was the linearly independent data samples, and the parameters of our network. Okay? By replacing this into our equation from before, and assuming that we're perfectly interpolating the labels, so we get perfect training, perfect accuracy, we can label everything, what gives us this. So this is that linear equation we want to solve. That'll give us a global minimum. We put this in. Now we have X times X transpose times alpha equals Y. And that gives us a unique solution. We can uniquely find the global minimum. And what we do is we form a kernel matrix or a gram matrix, K, that's equal to X times X transpose, plug that in, and we know how to solve this. It's a kernel trick. So it turns out that this kernel solution is exactly the minimum L2 norm solution of our equation that gives us the global minima. Right? Because there is an infinite number of solutions to this equation that'll give us a global minimum of a possible space. But SGD converges to the minimum L2 norm solution. And that's very interesting. And it may be some sort of regularization, some sort of implicit regularization that we have a minimum norm solution being found by SGD. The issue is minimum norm doesn't really tell us anything about generalization. They found that on MNIST, they had a norm of around 200, and that gave them some result. And then they did the same thing, but they applied Gabor wavelets to the input images first, and that gave them a much higher norm, but a factor of 2 lower test error, right? So much, much better generalization performance with a higher norm. So the norm doesn't really help us when we're talking about generalization performance, but it is an interesting analysis that SGD converges to minimum L2 norm. Cool. So what are the final conclusions, final takeaways from this paper? We discussed about effective capacity of neural networks. So hopefully you have an idea of what it means for a neural network to be able to represent possible functions, right? Neural network is a functional mapping. It can represent different functions, and this idea of effective capacity. Successful neural networks are large enough to shatter the training data. So even if we have a completely random labeling of the data, neural networks' representative capacity is enough such that we can shatter any possible input data, right, with the ones they investigated, up to over 1 million samples. Another interesting conclusion is that optimization continues to be easy, even when generalization is poor. And this was very surprising because they thought that there has to be some inherent connection between how easy we can find a solution and how good that solution is. And what they found is they can converge to a solution very quickly on the training set and perform terribly. Or they can converge very quickly and perform very well. Right? So the connection between being able to optimize easily and being able to generalize well is not as closely related as they initially thought it would be. We talked about how SGD may be doing some sort of implicit regularization by converging to solutions with minimum L2 norm. And the final conclusion, the final takeaway is that these traditional measures of model complexity when we're talking about VC dimension and things like that, really struggle to explain the generalization of larger neural networks. And unfortunately, they themselves do not present any better measures, and they don't know any better measures. But they at least show that these traditional measures really struggle to explain generalization, and sort of put a call out to the community that we should try and come up with a way to better measure generalization performance from a theoretical point of view. Cool. And that's the end of the...
Okay, very good. There used to be a class. That's interesting. So I have